Hello there, Mr. Sutton here, bringing you the AB Calculus Derivative Extra Practice Number 1 Solutions. For this derivative, we just need to use the power rule. So going from left to right, we've got 3x squared minus, well, let's see here, this is going to be 6 times 5 halves, which is going to be, let's see here, 6 divided by 2 is 3, times 5 is 15, so minus 15x, and then we have to do 5 halves minus 2 halves, so this is going to be x to the 3 halves. And then that 1 is just going to become a 0 when you take its derivative, so this is our answer. On this one, we can save ourselves a little bit of trouble with the derivative if we apply the log rule inside here. So ln of e to the something is just going to be the something. The ln and the e cancel. So this is really just cosine of 2x plus 4. And this is a chain rule. We have cosine of something. The derivative of that is going to be negative sine of something, negative sine of 2x plus 4. But we still have to multiply by the derivative of 2x plus 4, so we're multiplying by a tail of 2. To take the derivative on this one, we're going to need to use the quotient rule. So that would be u prime v minus uv prime over v squared. Let's set up the box and ribbon to help organize this. I have my numerator of cotan of x squared, denominator of 8x to the 10th, and now the derivatives of these. For the cotan one, we're going to have to use the chain rule. The outer function is going to be cotan of something. Derivative of that is negative cosecant squared of something, x squared in this case, times the derivative now of the x squared, which is 2x. Over here, derivative is just going to be the power rule, so this is going to be 80x to the 9th. Multiplying this out now, we have a big fraction. Upstairs, u prime v, that's going to be negative cosecant squared of x squared 2x times 8x to the 10th. Going the other way on the ribbon, we've got cotan x squared times 80x to the 9th, and we're subtracting all that. And then we're dividing by this stuff squared, so 8x to the 10th squared. For taking this derivative, I'm going to make my life a tiny bit easier in the beginning by simplifying this ln of x squared term. I'm going to pop out that 2 to write 2 ln of x. And now at this point, I'm going to have to use the product rule, u prime v plus uv prime. Let me set up the box and ribbon for these two terms. So we have 2 ln of x and cosecant squared of 3x. Derivative of 2 ln of x, that's going to be 2 over x. And by popping out that 2 in the beginning, we avoided a little bit of a chain rule there. For this next one, we have the outer function is something squared. The squaring happens first, or at least on the outer level. So that's going to be 2 times the something to the first power, so 2 times cosecant of 3x. Now we have to multiply by the derivative of cosecant, the next function in. Right now we've got cosecant of something, so that's going to become negative cosecant of something, cotan of something, the something being 3x on this one. And then finally we multiply by the derivative of 3x, which is 3. Putting it back together, we've got 2 over x times cosecant squared of 3x plus 2 ln of x times all of this stuff in the lower right. On this one, we're trying to take this derivative here. I've got a chain rule going on. Outer function is arc sine of something, so the derivative of that is going to be 1 over the square root of 1 minus something squared. In this case, that's pi minus x squared that's being squared. Now we have to multiply by the derivative of the something of pi minus x squared. Pi is just a constant, so that becomes 0. Minus x squared's derivative is going to be negative 2x. For this derivative, we're using the chain rule. We have 1997 to the something. That derivative is going to be 1997 to the something times ln of 1997. Now we have to multiply by the derivative of the something of x squared. That's going to be a tail of 2x. To make our lives easier on this one, we're going to use log rules to cancel some things out. Ln and e are going to cancel, leaving us with just the exponent here, x arcsecant of 4. But now, when you're taking the derivative of this thing, the key here is recognizing that arcsecant of 4 is a constant. It's actually a constant. So if you're taking the derivative of x times a constant, you just get the constant, which in this case is arcsecant of 4. To take the derivative on this problem, there's really nothing else for it but to go left to right and just use the chain rule here. It looks like there ought to be some kind of shortcut, but there really isn't. So starting with the tan cubed term, this is actually a chain rule with something cubed as the outer function. So the derivative of something cubed is 3 times something, tan being the something, squared. But now we have to multiply by the derivative of the inner function tangent, so we're multiplying by secant squared. Next, we're going to do the same thing pretty much with cosecant. So our outer function derivative, that's going to be 3 cosecant squared of x. Now we multiply by the derivative of secant, which is negative cosecant x cotan of x. And then derivative of 2 is just 0, so we're not going to write it. On this problem, the key thing to notice on this one is that we have y values all over the place, well, at least in 2 different places. Since we can't isolate y, we're going to use implicit differentiation. So anytime I take the derivative of something with a y, I have to multiply by a tail of y prime, or dy over dx, because y is considered an inner function of x. All right, so going left to right here, derivative of x to the pi, well, this is really a variable to a constant, so we're going to use the power rule here. This is going to be pi x to the pi minus 1. Next, derivative of pi to the y. This is an exponential function. This is going to be pi to the y times ln of pi times dy over dx, since we took the derivative of something with a y. And finally, this is going to equal, on the other side here, 6y times dy over dx. Next, we get the dy over dx's to one side and other stuff on the other side. So this pi to the y ln of pi dy over dx term, that can stay on the left. We're going to subtract 6y dy over dx to get it over there with the other dy over dx term. And this pi x to the pi minus 1, we're going to subtract that to move it to the other side, since it does not have a dy over dx. Now we did this so that I can factor out my dy over dx. That's going to leave me with pi to the y ln of pi minus 6y inside that parentheses. And to isolate dy over dx, we just divide both sides by this parentheses. So that's going to be negative pi x to the pi minus 1 divided by all of that stuff in that parentheses. And there is our answer. To make our lives easier on this one, before we launch into a chain rule, we're going to start by simplifying with log rules. So since I have ln of something to an exponent, I can pop out the exponent in front. So this is really just x times ln of 10. And if you're taking the derivative of x times a constant, using the line rule, you just get the constant. So this is really, for a derivative, is just going to be ln of 10. For this problem, since we have variables in the base and the exponent, the only way to do this is with logarithmic differentiation. So we're going to start by taking the ln of both sides. That gives me ln of y on the left side, and here's why I did it. On the right side, taking the ln of this expression pops out that exponent of ln of x. So that comes down to frolic with the other mortal terms here that are not exponents. And then we have ln of the base, ln of cosine of 2x. At this point, so taking some derivatives, on the left side we're going to have 1 over y, dy over dx. Again, y is an inner function of x, so we have to do a dy over dx tail, taking that derivative. On the right side, we've got the product rule. I have ln of x and ln of cosine of 2x. Derivative of ln of x is 1 over x. This derivative right here, I'm going to be using the chain rule. My outer function, I've got ln of something. Derivative of that is 1 over the something, 1 over cosine of 2x. But now I have to multiply by the derivative of cosine of 2x. That's going to be negative sine of 2x times a tail of 2. We have that inner derivative of 2x. All right, let's move some things together here. So u prime v, multiplying this out with the product rule format here, we've got ln of cosine of 2x over x. And then going the other way, I'm going to condense this stuff quite a bit. So sine of 2x over cosine of 2x, I'm just going to write that as tan of 2x. I didn't have to, but I'm feeling fancy today. And then we'll also have an ln of x and a negative 2. So this will be negative 2 ln of x tan of 2x. At this point, I still need to isolate dy over dx. So to do that, I multiply both sides by y. So I'll just put y times all of the stuff on the right side in a parentheses. And the directions did not say I had to put things in terms of x. So based on the directions, I could leave it this way and actually be done. However, if I do want to express this in terms of x, then I would replace this y with the original function, cosine of 2x to the ln of x, like so. And then I would have everything in terms of x.